Hello everyone. So we are back to our tutorial. So this is 10th tutorial class. In this we will be discussing advanced plasma diagnostics. We will be covering topics like atomic emission, spectroscopic analysis, Langmuir probes and broadening mechanisms. Emission of spectral lines allows you to identify the species. So when electrons are in excited states and they return to their lower states, they emit photons, as you all know, and because the energy levels are very specific to specific atoms, the wavelengths are also very specific and they are the signature of the atoms which are emitting, like fingerprint. Now each element or ion has unique emission lines, this H alpha, H beta, you see the very particular wavelength. So whenever you do the measurement, irrespective of space, you will be getting these emission lines. Now how do you then identify the species from the emission lines? Although they are characteristic of specific atoms, then just seeing the lines, how do you identify that the line belongs to a certain atom? So for that, once we have recorded the emission spectra, we need to go for database like NIST atomic spectra database that is available so far freely in internet. There you can see all the lines specific to specific atoms in the periodic table. So as I have told that every atom has emission lines, set of emission lines at particular wavelengths. So whenever you are observing a set of spectral lines and you are trying to match those set with the database that you are having, you will see that they are matching with a particular atom's emission line. So just comparing and matching that, you can identify which atom or molecule are emitting those lines. Now it is always a question that whether argon in neutral state or argon ionized, they will be having the same energy levels or not, because after all they all are argon, one is just not ionized and one is ionized. Actually, in the spectral database, argon 1 means argon atom and argon 2 means the first ionized argon. Now when you are removing an electron, the energy level structure is reorganized and that makes the emission lines corresponding to ion and atom to be different. So you can get ionic lines as well as you can get atomic lines, and ionic lines will allow you to identify the ions, whereas this atomic line will allow you to know the neutrals which are present there. And if you are getting these ionic lines, you are sure almost that they are getting ionized, because otherwise you will not get the ionic lines. And suppose you do have one filter which can band pass the wavelength which is around the ionic line, one ionic line. Okay. So if you use that filter and capture the image of the plasma, then you will be able to identify the zone where very high temperature exists, because Ions are there when temperature is sufficiently high so that it can form the ions. So the region where ions are present in good amount, they are definitely the high temperature zone. So these are different techniques that experimentalists use to identify various reactions that are happening in different zones, because as you know, suppose some product is coming up out of certain reaction, and that is also in very high temperature excited state, they are emitting. So if you focus on a particular line, on a line which is very particular though to that species that is generated, then from the image itself you can identify the zones where this reaction is happening, because there only you will get those lines, rest of the place you will not get. So it allows you to identify the reaction zones and spatiotemporal evolution of the reaction kinetics. So this is a very powerful tool, although it looks simple, but it is a very powerful tool to diagnose the plasma kinetics. Now you know, rotational and vibrational transitions produce bands, and they are very characteristic to the molecular transitions. Okay, so like we are very frequently encountering this nitrogen molecule OH radical when you break the H2O. So H and OH it breaks. Now nitrogen is very often encountered. The main reason is that nitrogen is having a triple bond, and breaking the triple bond is very difficult. It is a very strong bond. So even though if you raise a very high temperature where rest of the atoms are already ionized, you may get a significant fraction of N2 molecule which are present there, and they are emitting their characteristic band spectra. So now what I do, I come to a practical example. This is one, you know, this nitrogen plasma jet emanating from an arc plasma device. So this is the nozzle exit, plasma is coming out, and this setup is actually a diagnostic setup to understand the enthalpy profile from the heat flux that is getting recorded using a calorimeter. So this plasma column, because it looks like a column, so very often we call arc plasma jet as a plasma column, that is emitting radiation. Now from just visual look at this jet, it is not possible to tell which zone is at what temperature. But you know, if you image this using CCD camera, then camera records the intensity from different zones, and you know, calibration facilities there in many of the, you know, imaging instruments. There you can use color codes, so that you come to know that if this is the, you know, color band that you are using, this temperature is the highest temperature and this is the lowest temperature, and whatever intensity you have got throughout the jet, you are now presenting that as per the intensity, as per the color code. So highest temperature zone will be presented by, say, this red one, and then the lowest temperature will be your blue one, and which is beyond this red temperature that you have presented here, that may be coming as just white without anything. Now what we have done, we have just plotted the lines over here, you know, which presents the isothermal contours. Okay, so this contour is showing that along this contour you will have a same temperature around 7700 degree Kelvin, and then as you go down, as you are seeing the green and even the blue is there, so this is telling you the jet length and intensity along the axis. You are seeing that is also not constant. For example, you see that here the color is more towards red and here it is yellowish. So temperature at this zone is less than the temperature in this zone. But you know, this advantage of this technique is that at a single glance, actually in a single snap, you are able to map the temperature distribution over the whole jet. You are not making any effort of collecting light from every point, then making a Boltzmann plot, or then trying to identify the temperatures, not like that. You have mapped the intensity and you are assuming that that intensity is proportional to the temperature, and roughly you are mapping the temperature within this zone. Now, when you have mapped through this color code, then you know this is the red zone and this is the blue zone. You want to know the temperature over here. Once you know the maximum temperature over here, then as per the color code scheme, you know the rest of the temperatures. So, in this, what is the maximum temperature? So, that red is here and you collect a light from here and you do proper emission spectroscopic analysis and find out the temperature. So, here in this case, we have done that and we have presented these as this 7700 Kelvin. Once we have done that, we know this is 7700. So, accordingly this jet's color scheme allows you to find the temperature at other places. Okay. So, this is how we are doing, but this is a very rough and approximate idea, but this gives you a good idea about the kind of distribution that may occur within the jet. And if you are really interested to find the accurate temperature, definitely you need to go for the proper spectroscopic calculation like Boltzmann plot. Now, there is another way of getting the temperature identified, like that. If it is a molecular spectrum, as I told you, this is a nitrogen plasma jet, and you will get a copious amount of radiation from the molecular rotational vibrational spectra. Now, nitrogen is having very popular bands. This is part of the nitrogen second positive system, and you can well simulate this band from theory. And we have done that. Nowadays there are many softwares are available which you can use to get this spectra from simulation. Now, you have done that, and then what you are doing, you have got something from experiment. This is which is recorded by our spectrometer. And what we are trying actually, in the simulated spectrum, we are now just varying the temperature. And we are trying to get the simulated band, and we are trying to find where it matches very close to the experimental one. And we are changing the temperature, and we are seeing that when you are setting the temperature to be say 7700, then the experimental and simulated spectra are matching very perfectly. So, then we say that okay, the temperature of the plasma at the location where from the light has been collected is this much. So, what we are doing, we are simulating the spectra and matching that with the experimental one. So, this is a trial and error, and when the temperature at which you are getting the best matching of the experimental and simulation spectra, you are telling that okay, the temperature of that zone is this much. So, this is one technique that is accepted in in this area as finding the temperature of plasma. And earlier one, what I told, it is a very easy way to map the temperature distribution all over the jet through a single snap. Okay. So, although the temperature distribution may not be very accurate, but it gives a very good idea about the distribution of temperature within the jet. So, now I come to the concept of PLT, as I have told number of times in our regular class that this occurs when the upper lying energy levels are in equilibrium as per the Boltzmann distribution, but the lower lying levels are not. And this happens for a temperature at a temperature Te and density N. This is the kind of relationship required for the PLT to hold. But in case of PLT, what happens, when you go for a Boltzmann plot kind of thing, then the linearity is observed for certain lines and that is violated by some other lines. And you are seeing that here I have plotted as a function of the upper energy level here, and you are seeing that when the upper energy involves lower lying states like here, this 1 and 2, they are always very off from the line that has been drawn over here. And this is not seen in only one instance. This is seen number of instances whenever you catch the you capture the spectra and you try to analyze using Boltzmann plot. You always see that these two lines are not as per the Boltzmann plot. So this is for one system. For other system, so also you may encounter such kind of thing that many of the lines are falling on one line, but some lines, specifically those which are involving the upper lying states at lower energy levels, they are not following the linear plot of Boltzmann plot equation. So this is how the PLT or LT which exist in a system are reflected in this thing. See, the beauty is that something is happening, in quantum levels, in quantum scale, and those things neither we are able to see nor we know what is exactly happening over there. But this is a thing which we are just plotting using our computer, and we are able to see what is happening there in the quantum levels. So probing the quantum phenomena, what is happening in the electronic energy levels, we are just able to see, just capturing the intensity of the line they are emitting. So this is something, if you think deeply, you will find the significance of this technique. Now, the hydrogen spectral series that we are starting since our school days. We know that Lyman, Balmer, Paschen, Brackett, Fund. There are several series depending on the level where the transition terminates. Like the final level n equal to 1, you call Lyman, n equal to call Balmer, then n equal to 3 is Paschen, like that. And the emission that you get in the Lyman series is it is in UV, Balmer series in visible, then Paschen, Brackett, they are in infrared, Fund also in infrared, and where you apply this Lyman series in UV astronomy, then this Balmer series is invisible, and we are using that very often. Now, I'll show you one example of that. This is one already I have shown you in our regular classes. So there are two lines, H alpha and H beta. Their wavelengths are shown over here, and one line that is at 656.3 nanometer, as it appears in the overall spectrum, looks like this. You are seeing this rectangular zone, this peak, and when you expand this peak, this is the detailed distribution of the intensities over the wavelength. Now, you know that it is 656.3 nanometer, and here what you are seeing, it is bit different from that. So that is instrumental shift which occurs when you capture the spectra. So each instrument will have some shift, and you need to subtract that to know the exact wavelength. So in this case, the peak has to be at 656.3 nanometer, and you are seeing that it is not there. So exactly where it is occurring, you note that thing, and where it should appear, you know already. So the difference is the shift of the instrument itself. So you have to subtract by that amount for all wavelengths to exactly mark the wavelength of the lines that you have captured. Now, finding the plasma parameters, we have electron temperature, ion temperature, and electron density. For electron temperature, I am just summarizing what we have understood in our classes, that Langmuir probe IV characteristics can provide you T in low temperature plasma. Boltzmann plot technique can give you T in thermal plasmas. Then this this derived from exponential region of the electron current. This is for the IV curve. Okay, the T you can determine from there. Now ion temperature can be obtained from the Doppler broadening, because ions are moving at the same time they are emitting. So the wavelength that you are recording is getting shifted due to the motion of the ion, and that that change in frequency is due to the Doppler effect depending on the velocity. So the ion temperature is connected to that. So you can determine the ion temperature from the Doppler broadening that you are observing in the line. The Doppler shift also you can use for finding the temperature. Now electron density, in for electrons you can determine using Stark broadening. One example we have already shown in our regular class, where using the H beta line or H alpha line to find out the electron density. Now what a Langmuir probe measures? This measures the potential, electron density and electron temperature, and it can give you floating potential as well, but it cannot measure ion energy distribution. Key features of the IV curve: the knee in the curve gives you plasma potential, floating potential when net current is 0, and it is usually more negative than the plasma potential. What are the limitations of Langmuir probe? You cannot use it so easily in magnetized plasma, because the magnetic field disturbs the electron kinetics. Always the magnetic field, the moment it finds an electron, it tries to trap it and make it rotate around it, and if the B is strong enough, then the radius of gyration may be smaller than the probe diameter. So in that case, the whole probe is not collecting the electrons, so you can understand that our estimation may go wrong. Also, most of the cases we are assuming that electrons are following a Maxwellian distribution, which may not be true for many of the low temperature plasma systems. So in summary, the plasma diagnostic techniques: atomic species diagnostic method is emission spectroscopy. Principle is unique emission lines. So to identify the species, if you want to find the electron temperature, you can go for Langmuir probe or emission spectroscopy in case of thermal plasma. So IV curve exponential region in case of Langmuir probe, we will give you the electron temperature. Boltzmann plot technique can give you the electron temperature in thermal plasmas. Ion temperature you can find out from Doppler broadening, and thermal motion broadens lines in case of your in case of your line broadening for the species that you are considering. Then electron density you can determine from Stark broadening or Langmuir probe. Line width basically in case of Stark broadening is proportional to NE. And then plasma potential you can find out from Langmuir probe, from the knee in the curve, and molecular temperature from rotational band fitting, as I have explained, and you can find out from the spacing between the rotational lines. So this summarizes the spectroscopic techniques that we can use for plasma diagnostics, and this is our this Child's law that we I want to just tell you that current is proportional to voltage, B equal to IR, that is the ohmic region. So voltage what you are getting, depending on the resistance and current, it will be there. So relationship with voltage and current is linear when your R is constant. But this is not always the case. As you know, in arc it is showing a negative VI characteristics. Now in plasma, in the sheath region, you have space charge dominates, like the positive charge are dominated in the sheath region. Similarly, we are going for a vacuum tube, which is considering the electron motion, then the space charge of electron near the cathode, that is controlling the current. How it is? For example, the cathode which is emitting. when the electrons are emitted, because so many electrons are surrounding, they are emitted almost with the zero velocity. Then the variation in potential near the cathode is almost del V del x is 0 if x is the direction of axial direction. So V is 0, del V del x is 0 at t is equal to 0, at x is equal to 0, and then the phase charge is moving and constituting the current. So in those cases, the VI relationship is not linear. And what kind of relationship it follows, this numerical 29 tells you. So I'll just tell you that thing. We have several assumptions that it is a planar geometry, only one type of charge carriers, it is either electrons or ions. Then zero initial electron velocity, collisionless plasma, and space charge dominates. So electron, in case of these vacuum devices, and ions in case of seed. So the derivation is very simple. Through the potential drop in that region, the energy is gained is EV, and that is causing the velocity of the particles. So from there you get a relationship between the here I am considering the electrons here in this, and for seed region you should consider the ions. So here you get a relationship with the velocity and the voltage applied. From there you get your number density, because J is equal to NeV. So J by EV. So this is the the relationship. Now from Poisson's equations, del square V is equal to minus rho by epsilon 0. So you apply it over here, and what you get actually d2V dx2 is equal to this one. If you use this one. Now using that, you are coming here, then you multiplying both sides by dV dx, just mathematical manipulation, and you can get this relationship. And C is this quantity which is circled here. Now what is happening? You are using this relationship, and you are using the boundary conditions that at x equal to 0, V is equal to 0, and dV dx is 0. So this similar thing can be applied in case of seed as well. So that gives you d equal to 0, and you get this relationship, and you integrate, and finally you get this is the relationship when you put the value of C, that is over here, that J is equal to V to the power 3 half. So the relationship is not proportional to V, it is proportional to V to the power 1.5. So this is called Child's law in case of your electron devices. Now in case of your plasma seed, then also this kind of situation arise. So and you will get a current voltage relationship, similar relationship you will be getting over there, and this D is not that cathode anode distance there. This is the your space charge width in case of your ion seed. So these are key differences for Child's law in vacuum devices and plasma seeds. Carriers are electron in vacuum devices, and in plasma seed they are ions. Initial velocity is 0 for cold emission, but in plasma seed you have already learned that we need to have a velocity, Bohm velocity, for the seed to form, for seed to exist. And the scaling goes as like this. So V to the power 3 of law is followed in case of vacuum diode as well as for the plasma seed. So this is very interesting. So Child's law we all know probably that works in case of vacuum devices, but for plasma seed, this you see that this the same way it works. Only thing is that this D is replaced by the seed width. Okay. Now geometry, fixed electron spacing, electron spacing D, that is there. Here the seed thickness actually depends on the potential. So it adjusts with the potential. So that is the difference, and I hope that you have got the insight about this current voltage relationship, the scaling that it does with voltage, and the information that you have got in this tutorial. I hope you have got enough insight about the problems. So I stop here and meet you in the next tutorial in the next week. Thank you.